Okay, in this video we are going to finish up section 6-3, trig functions of any angle, and we're going to talk about this last bullet point, evaluating the trig functions of real numbers. So here it says to define a trig function of a real number rather than an angle, let t represent any real number. Then imagine that the real number line is wrapped around a unit circle, as shown in the figure. Now, unit circle means it has a radius of 1. So anywhere on this circle that we draw a radius, we know that that radius is length 1. That's our unit circle. Note that positive numbers correspond to a counterclockwise wrapping, just like when we opened our angles, and negative numbers are a clockwise wrapping. So here off to the side in blue, they have, this is the number line, just the real number line, 1, 2, 3, 4, and up. And we're going to start to wrap that number line around the unit circle, a circle of radius length 1. If we do it clockwise, those would be our negative angles. Here's our number line again. These would be our negative numbers to the left of 0. And we're just wrapping those around the circumference of the circle. Now, as the real number line is wrapped around the unit circle, each real number corresponds to a central angle theta in standard position. Moreover, because the circle has a radius of length 1, the arc intercepted by an angle theta will have directional length. S is equal to r times theta, and since the radius is 1, that's going to be 1 times t or t. The point is that if theta is measured in radians, then t, the length where we are on the number line, that real number, is equal to the angle in radians. So you can define the sine of t as sine of t is equal to the sine of t radians, or cos of t is the cosine of t radians, tan of t is tangent of t radians, and so on. Furthermore, because each t value corresponds to a point, x comma y on the circle, that's a good point. As we move around the circle, every point on this circle is an x and a y coordinate. And because our radius length is 1, all these points on the circle is the sine of t is opposite over hypotenuse, or y over 1. So our sine value is the y coordinate. The cos is adjacent over hypotenuse. Here our adjacent side is the length of the triangle of x. The hypotenuse is still 1. That's the radius of our unit circle. X divided by 1 is x. So the cosine is equal to the x coordinate. And the tangent value is the y coordinate divided by the x coordinate. So let's see, here in our unit circle, let's just concentrate now on the first quadrant. As we open up our angles, this would be 0 degrees, and then we have our first special angle, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. And we can also have those in radian measure. I'll do those in red. 1/6 pi radians, 1/4 pi radians, 1/3 pi radians, and 1/2 pi radians. And now, when we look at it in this way, each of these points on the unit circle is an x and a y coordinate. The x coordinate is cosine, and the y coordinate is sine. And we could set up, if I dropped this side down here, we know the radius is length 1, so I could say the sine of 30 degrees, or the sine of pi over 6 radians, would be opposite over hypotenuse. And since we have the hypotenuse, we can solve for that missing side. And it's going to turn out to be 1/2. And I could move up to this next point. And I have my 45 degree angle here, or 1/4 pi radians. And I could set up a triangle to solve for the sine of 45 degrees, or the sine of 1/4 pi radians. And if I solve that, that's going to be, for sine, my y coordinate, square root of 2 over 2. And if I come up to the 60 degree angle, or the 3rd pi radians, set up a triangle, solve for sine. If I do that, I'm going to have a y coordinate of square root of 3 over 2. And if I come all the way up here, again, if we remember, our circle is a radius length 1. If I wanted to find the coordinates of this point, I went left or right 0, up 1. So there, our sine value of 90 degrees, or 1/2 pi radians, is 1. And if we look as we go up, we have the square root of 1 over 2, the square root of 2 over 2, the square root of 3 over 2, and up here to the square root of 2 over 2. Or I mean the square root of 4 over 2, which divides out and becomes a 1. And again, these are our cosine or our sine values. To find the cosine values, we could just set up another triangle and solve for this adjacent side. And this adjacent side is going to be the same as our x-coordinate. And when we start to pick up on the pattern from the table that we had seen in previous sections, we're just going to reverse course here. And if we plug in this first coordinate here, our height, our y value here would be 0. So we go 0, a half, root 2 over 2, root 3 over 2, 1. To get the cosine values, our x-coordinates, we reverse the process. 0, 1/2, square root of 2 over 2, square root of 3 over 2, square root of 4 over 2, which divides out to 1. So there's our first quadrant. We have our special angles, 0, 30, 45, 60, and 90, also in radians. And we have the x and y coordinates, which for the unit circle happen to be, our cosine and sine values. And now that we have the first quadrant, we can reflect that around to the second, the third, and the fourth. So as we start going around, we left off at 90 degrees. Let me get back to the blue pen. If we keep going, our next angle here would be 120 or 90 plus 30. 90 plus 45 would be 135 degrees. 60 plus 90 would be 150. And then we get to a half circle, 180. And we can also measure those in radians. So here we would have 2/3 pi. 2 pi divided by 3. Then would be 3/4 pi. 3 pi divided by 4. And 5/6 pi. 5/6 pi. And in radian measure, a half circle is pi radians. So there we have our angles for the second quadrant. Our sine and cosine values are going to be the same, but in quadrant 2, our x values are going to be negative. So I can copy these points as they are and just make all my x values negative. So up here at 120 degrees, I'm going to have 1/2 square root of 3 over 2, but because we are in the second quadrant now, this x value is going to be negative. Come down to the next one. Square root of 2 over 2. I'll start to write on a little angle here. Root 2 over 2, root 2 over 2. And again, our x value is negative. And here at 5/6 pi radians or 150 degrees, that's just a reflection of this set of coordinates into the second quadrant. So we're going to have our root 3 over 2, comma 1/2, and that x coordinate is negative. And we're back here right on one of our axes, so the coordinates of this point would be -1, comma 0. So there's our first and second quadrants for the unit circle. Let's keep working our way around, get down here into the third quadrant. 180 plus 30 is 210. 180 plus 45 is 225. 180 plus 60 is 240. And then we get to 270 for the negative y-axis. And we have the measures in degrees. We can also find them in radians. Here we'll have 7/6 pi radians, or 1 1/6. 5/4 pi radians. 4/3 pi radians. And then 3/2 pi. 3/2 pi radians. Now our coordinates are going to be the same, but now since we are dealing with quadrant 3, both the x and y values will be negative. So here we're going to have, I'll switch back to black to keep it consistent. This will be negative square root of 3 over 2, square root of 3 over 2, comma, -1/2. Here at 225 degrees, it's root 2 over 2, negative, and another negative root 2 over 2. And then finally, our x coordinates -1/2, comma, negative root 3 over 2. So we're working our way around. We only got one more quadrant to go, and let's get our degree measures first. 30 plus 270 is 300. 45 plus 270 is 315. And then we have 330. And we started at 0 and we're back to 360, a full run around the unit circle. And let's do this in radian measure. So first we're going to have a 5/3 pi radians, 7/4 pi radians, and 11/6 pi radians. 11 pi over 6. And again, our coordinates will be the same, except now we're down here in quadrant 4, so our x values will be positive, all y values will be negative. So here we are at 1/2 x coordinate, negative √3/2 for our y. All the quarter ones are √2/2. Here our x value is positive. √2/2 for our y value, and that one is negative. And then we finally have here √3/2, comma, -1/2. Now, if we always keep in the back of our mind that our x value is the same as cosine, the y value is our sines. You know, right here we have a bunch of values of trig functions. What is the cosine of 225 degrees? Well, here's our 225 degree angle. Our cosine is the x value, -√2/2. What is the sine of 5/6 pi radians? Sine of 5/6 pi radians, well, here's 5/6 pi radians. Our sine is the y coordinate, so that would be 1/2. And if we remember that we have sine and cosine, we can divide these to get our tangent functions values. And since we have those three, they all have reciprocals. So if I wanted the cosecant of 30 degrees, cosecant of 30 degrees, we don't have cosecant, staring us in the face, but we know that cosecant is 1/sine. So if I find the sine of 30, which is the y coordinate right here, 1/2, if I want the cosecant there, I just turn this upside down. 1/2 becomes 2/1. So once you get this, all memorized and learned very well, this is actually the answer to 96 different pre-calc questions. All the trig functions values at these major important angles. So let's see here. In example 8, we have evaluating trig functions. In part A, it says evaluate f of t, then that's equal to sine of t for, they give us two different t values. For t equals 1, and again for t equals 7/2 pi. So for part A, it says find f of t is sine of t for t equals 1. So we want to find the sine of 1. And 1 is not a nice easy measure on our unit circle. Remember, we're dealing all in radians here. We're in fractions of pi. 1 is not a good fraction of pi. So this one we would just do on the calculator. We want to make sure we're in radian mode, and we want to hit 1 and then the sine key. And the calculator will spit out our answer. We always round to 4 decimal places, and that is 0.8415. The second part of that question, they say they want us to evaluate that for 7/2 pi. The sine of 7/2 pi, or I like to write it as a mixed number, the sine of 3.5 pi. This one we should be able to do on our unit circle. So the sine of 3.5 pi. Well, a full lap around is 2 pi, and then another half circle would be 3 pi. So 3.5 would take us to the negative y-axis. And I forgot to put in our coordinates here. This is 0 x coordinate, -1 on the y. And for this problem, we are finding the sine value at this angle. So the sine value is our y coordinate, or -1. So that's equal to -1. Let's see here, part B. It says evaluate cos of t for t is equal to -2/3 pi. So we want the cos of -2/3 pi. And it says which corresponds to this point on the unit circle. So let's see, -2/3 pi. Let's go back to our unit circle. -2/3 pi would be, here's -1/3. negative 2/3 would take us right here. And our x-coordinate is negative 1/2. Our y-coordinate is negative root 3 over 2. Negative 1/2, negative root 3 over 2. They're asking us for the cosine value. Well, the cosine value is the x-coordinate. So that would be negative 1/2. Or negative 0.5, however you want to write it. Now, if we think about domain and range, domain are the numbers that we put into the unit circle. Remember back at the very beginning we were talking about here's our number line, and we're wrapping it around the unit circle. As we go around once, we'll just keep overlapping and overlapping. Same thing with negative. We're wrapping our negative number line around in a clockwise fashion, and that tells us that our domain is all real numbers. The domain of the sine and cosine functions are all real numbers. To determine the range of these two functions, consider the unit circle shown down here in the figure. By definition, sine of t is the y-coordinate, cosine of t is the x-coordinate. Moreover, because x comma y is just a point on that unit circle, you know that the y values will always fall between or equal to negative 1 and 1. And the x values will always fall between negative 1 and 1. And we see down here with this red marking on the side, our y values go from up here to down here. The lowest we ever go is negative 1. The highest we ever go is positive 1. Same thing for the x coordinates. From the center here, the farthest we ever head out this way is to positive 1. The farthest we ever head to the left is negative 1. So sine and cosine both have a domain of all real numbers and an output or a range of numbers falling between 1 and negative 1 or equal to 1 and negative 1. So the values of sine and cosine range between negative 1 and 1. Adding 2 pi to each value of t in the interval 0 to 2 pi just completes a second revolution around the unit circle. The values of sine of t plus 2 pi and the cosine of t plus 2 pi correspond to sine of t and cos of t. Remember, it's just another lap around the unit circle. Similar results can be obtained for repeated revolutions, positive or negative. And that just gives us this general result. We can take the sine of some value t and add 2 pi times some integer n, like 2 pi times 3 or 2 pi times 7, 2 pi times 10, and it's always going to be equal to sine of t. And something similar can be said for cosine, for any integer n and any real number t. Functions that behave in this repetitive or cyclic manner are called periodic. These are periodic functions. So a function f is periodic if there exists some positive real number c, such that the function of t plus c is exactly equal to f of t. It's sort of like adding that t doesn't really change the output or the value of the function. And this is true for all numbers t in that domain. The smallest number, c, for which the function is periodic, is called the period of the function. And if we recall from an earlier section, we had even and odd functions. A function is even if f of negative number is equal to f of its positive corresponding counterpart. And it's odd if f of negative t is the negative function of t. And with the sine and cosine, these trig functions, cosine and secant are the even ones. If we have the cosine of a negative angle, that's the same thing as cosine of the positive angle. Or the secant of some negative value, and that's equal to secant of the same value. All remaining trig functions are odd. If we have the sine of a negative number, and if we did something like this, the sine of negative 30 is equal to the negative sine of 30. And the way I always approached this when I was in school was, if it's an odd function, you can almost sort of factor that negative out. I can take this negative out front and put it in front of the trig function, negative sine t. Same for tan and cosecant and cotangent. In the even functions, it's sort of like squaring a negative number and it goes away. This is the cosine of negative t, sort of like the negative doesn't really matter at all. So here's a couple problems for the huddle. The first couple, work with that on the unit circle. Pause the video, try the problems out, and then come back and check out the solutions. Okay, in the first problem here, it says find two solutions of the equation. Give your answer in degrees, somewhere between 0 and 360, and in radians, somewhere between 0 and 2 pi. Do not use a calculator. So in the first one, it says the cosine of some angle is the square root of 2 over 2. So if we remember on the unit circle, our cosines are x values. So we want to look at the unit circle and look for x values that have this value, square root of 2 over 2. So I got a nice unit circle right here. And remember, cosines are x values. We have a positive square root of 2 over 2. Where are x values positive? Over here on the unit circle, this part of the x-axis. So where do we have a square root of 2 over 2 for a x value? Well, here's our x value as a half. That's not it. Here's root 3 over 2. That's not it. But here we go. Square root of 2 over 2 positive for an x value. And we should also have one underneath. You know, here again, our x values are positive. Here's a positive 1/2. We don't want that. Square root of 3 over 2. Here we go. Square root of 2 over 2. What angles made that output possible? Oops. And they want the answer in degrees and radians. Well, right here, this square root of 2 over 2 happened at 45 degrees, or pi over 4 radians. 45 degrees, or pi over 4 radians. And down here in the fourth quadrant, we had the same values come out at 315 degrees and 7/4 pi radians. 7/4 pi radians. So there's the answer to part A. Now let's check out part B. The only difference here in B is now we want cosine of theta equal to negative square root of 2 over 2. So I can even slide the unit circle over here because cosines are x values. Now we want negative x values. And that occurs here in quadrants 2 and 3. So where do we have x values equal to negative root 2 over 2? Well, here's an x value at negative root 2 over 2. Yep, here's another one down here. So what angle measures made those outputs possible? 135 degrees. Down here in the second quadrant at 225 degrees. And in radian measure, that'd be 3/4 pi. And 5/4 pi. There we go. Okay, now in the next one it says find the point, you know, x comma y, on the unit circle that corresponds to the real number t. Use the result to evaluate sine of t, cos of t, and tan of t. Well, now they're telling us t is 1/4 pi. And they want us to find sine, cosine, and tangent here. So we're going to find the sine of t, the cos of t, and the tan of t. So we want to go to the unit circle and look at 1/4 pi radians. Well, right here's 1/4 pi radians. And we have a couple numbers here. Remember, cosine is the x value. So the cosine of 1/4 pi radians is square root of 2 over 2. The sine value is our y coordinate, and that's also square root of 2 over 2. From these, we can find tangent. And remember, tangent is equal to sine divided by cosine. Sine divided by cos. So here we have the sine and cosine values. Well, sine is the square root of 2 over 2. Cosine is the square root of 2 over 2. Anything divided by itself is 1. Or if you want to think, you know, fraction divided by fraction, invert and multiply. So I'd bring this denominator up and flip it to 2 over the square root of 2 and then multiply. These 2's would cancel, the square root of 2's would divide out, and we're left with 1. Here's the final assignment for this section, 6-3, day 3, page 485. It's just a handful of problems, not too many.